Hello, today I am going to go over the 2010 FAQ number 5. Consider the differential equation dy over dx equals 1 minus y. Let y equals f of x be the particular solution to this differential equation with the initial condition f of 1 equals 0. For this particular solution, f of x is less than 1 for all values of x. A. Use Euler's method starting at x equals 1 with two steps of equal size to approximate f of 0. Show the work that leads to your answer. Euler's method states that given an initial condition, differential equation, and step size, we can estimate a point xy. Using the equation, yn equals yn minus 1 plus h times f of xn minus 1 yn minus 1, where x1 equals x0 plus h, where h is the step size, and y0 equals y of x0. Approximate f of 0 with two steps of equal size given that x equals 1. To solve this problem, we're going to use the equation for Euler's method, which is yn equals yn minus 1 plus h times f of xn minus 1 yn minus 1. The step size, which is h, equals negative 1/2 since we're going to the left, and y0 equals 0, and x0 equals 1, as given by the initial conditions f of 0 equals 1. y1 equals 0 plus negative 1/2 times f of 1, 0. Plugging in 1, 0 into the differential equation 1 minus y, we get that y1 equals negative 1/2. y2 will equal negative 1/2 plus negative 1/2 times f of negative 1/2, negative 1/2. Plugging in negative 1/2 into the differential equation, we get that y2 equals negative 1/2 minus 3/4. y2, which is the same as f of 0, therefore equals negative 5/4. Part B, we're asked to find the limit as x approaches 1 of f of x over x cubed minus 1. To solve this question, we're going to use the Hospital rule, which states that if f and g are differentiable and g prime of x does not equal 0 on an open interval I that contains a, and limit as x approaches a of f of x equals 0, and limit as x approaches a of g of x equals 0, then the limit equals the limit as x approaches a of f prime of x over g prime of x. So, the limit as x approaches 1 of f of x over x cubed minus 1 equals f of 1 over 1 minus 1, which equals 0 over 0, which is an indeterminate form, which means that the Hospital's rule applies here. Using the Hospital's rule, we get the limit as x approaches 1 of f prime of x over 3x squared, which equals f prime of 1 over 3. Since we know that dy over dx equals f prime of x, which equals 1 minus y, and f of 1 equals 0, that means that f prime of 1 equals 1 minus 0, which equals 1. Therefore, the limit as x approaches 1 of f prime of x over 3x squared equals f prime of 1 over 3, which equals 1/3, which is the answer to this problem. So for part C, we're asked to find the particular solution y equals f of x to the differential equation dy over dx equals 1 minus y with the initial condition f of 1 equals 0. The differential equation is a separable differential equation because a separable differential equation can be written as a function of x times a function of y. Below are examples of separable differential equations, and we can see that the one given is a separable differential equation. We are asked to find the particular solution to the differential equation dy over dx equals 1 minus y. with the initial condition f of 1 equals 0. Since this is a separable differential equation, we can manipulate it to get the integral of dy over 1 minus y equals the integral of dx, which equals negative ln of the absolute value of 1 minus y equals x plus c. Plugging in the initial condition of f of 1 equals 0, 0, we get negative ln of 1 equals 1 plus c. Solving for c, we get that c equals negative 1. Therefore, negative ln of the absolute value of y minus 1 equals x minus 1. Multiplying both sides by negative 1, we get ln of the absolute value of y minus 1 equals 1 minus x. To find the particular solution, we're going to exponentiate both sides by e, which gets us 1 minus y equals e to the 1 minus x. Therefore, the particular solution is y equals 1 minus e to the 1 minus x.